Hello, welcome back. We're going to take today a simple paperclip that you can find anywhere, and we're going to explore kinetic energy and potential energy in slow motion using a simple paperclip. Now let me show you what I mean. We used to build these things all the time as kids. They're pretty fun. I actually still like doing it today. If you take a paperclip like this and bend it one time out like that, and then take the other side, the side that's coiled up, bend it one time out like that, and then bend this guy out like this, you sort of get a weird looking triangle. You can see I have several of them in that state like this. And then what you do, once you get it into this triangular shape here, what you do, make it into a triangle like this, and then you bend it out towards yourself. So you can kind of stand it up like this. And then what you do, and you can do it with any paperclip, by the way. I can take a smaller one. This is a smaller paperclip. You just open it up like that, so you have sort of a triangle, and you bend it toward yourself, again, so you could sort of stand it up. There. Now what you do is you attempt to close it back together and try to, with your fingers, you have to be very careful with your fingers, balance it so that it doesn't snap apart like that. Actually, it's difficult with these small metal ones. So I'm going to do it with the big ones. I found that these rubber or plastic coated ones are much, much easier. So what you can do is bend it. Here, that's much, much better. Bend it like this, and you spin it around, and with your fingers, you got to feel that sweet spot. You're going to mess up a few times, just like I have here. And so there you go. So it's kind of like ready to go. Now this paperclip has what we call a high potential energy. If I drop it, let's see what's going to happen. 1, 2, 3. And it bounces up like that. So that's really fun. Now, if you use the smaller ones, especially, this is coated as well, but not with the same material, it's a little hard to get it to kind of stay. I mean, you can definitely get it to work, but it's a little difficult. So 1, 2, 3, here we go. Of course, sometimes they don't always work. 1, 2, 3, and that one goes like that. So one more time, we'll do it just for giggles. All right, 1, 2, 3, here we go. There we go. Now I want to explore what's actually happening here, but before we do that, let's film it in slow motion. Let's get right up on top of it and see if we can learn something with regard to how this process of launching these paper clips actually happens. Now there's so much to talk about here. At the surface level, we see that this paperclip has a lot of potential energy stored before it hits the surface. The act of it hitting the surface dislodges the two ends of the paperclip and allows it to rebound and act almost like a spring, which then propels the paperclip up in the air. Now, from a physics point of view, it's a really great introduction to the concept of potential energy before the impact being converted to kinetic energy, which is the energy of motion as it launches up into the air. And so this is the law of conservation of energy in action. But beyond that, believe it or not, this is a really good analogy for how things burn, how fire actually happens. So when you think about it, oxygen is surrounding everything on my desk here in the air. And of course, the paper is sitting on my desk. And of course, if I bring a flame to the paper, it'll burn with the oxygen in the air. What does this have to do with paper clips? Well, the act of bringing the flame next to the paper gives an initial amount of energy to the oxygen molecules in the air and also to the paper, and causes them to collide with a lot of energy. And so it overcomes what we call an energy barrier. You see, the oxygen in the air and the paper, the fuel that's on my desk, they want to combine and go into a lower energy state, releasing heat and light. We call that fire. This wants to happen. But the only way the process can happen is if I give it an initial amount of energy to sort of start this chemical chain reaction. Also, you can see it in these paper clips. There's a springiness there, and of course it wants to convert that potential energy to kinetic energy, but the only way it can happen is by giving it an initial jolt of energy, which starts the process by unhinging the two ends of the paper clip. Then the process can complete. This is very analogous to activation energy in chemical reactions, especially fire. You need to give it a little bit of energy to start the collisions with such energy to begin begin the reaction to rearrange the electrons. Once the fire begins, then the heat and the light that are already there continue the reaction, and so we say the whole thing catches on fire. Another thing I find fascinating here is that as the launch happens, you can see the ends of the paperclip wobbling back and forth at a resonant frequency, right? That depends on the mass of the paperclip and the length of the legs of the paperclip. So there's just a ton of different things that we can learn from something simple like a paperclip. You can think of a spring. You can think of the natural coiled state of a spring. And this is what we would call low potential energy, because it's just kind of sitting there. It's not stretched or compressed, and so it's not going to do anything. So it has a low potential energy, maybe even zero potential energy. Now, if you take that same spring and coil it real tight, like this, so you squish it up like this, and you do that by applying some force in this direction, by pushing it up like this, then we say that it has a high potential energy. And it has a high potential energy. Why? Because it has the potential to do work or to move something. If I let this thing go, it's going to go boing like that, right? Now, what if we go the other way? Instead of compressing the spring, what if we expand the spring? Like this. We stretch it out like this. Well, same thing. I do that, but the opposite direction. I pull it in the opposite direction. But when I let it go, it's going to bounce back. So it has the potential to do some kind of work. So we're going to call this, again, high potential energy. Wrote PE twice. High potential energy, right? The point is that when you compress or expand the spring and then let it go, it's going to begin to move. It's going to convert that potential energy into motion, which is kinetic energy. Eventually, it'll boing back and forth, converting back and forth into potential and kinetic forms, and eventually it'll stop. And the only reason it'll stop moving is because there is friction internally between the atoms in the spring, and the rubbing will slow it down over time. But that energy goes into the thermal motion and agitation of the atom. So it's not like it disappears. It just goes into what we call the temperature of that spring. If you do that enough, even if you bend a metal back and forth over and over and over again, you'll see that it gets hotter like this. So we convert potential to kinetic energy in springs as well, and that is what is happening in this mouse trap right here, and that is also what is happening when we do when we have one of these one of these paper clips that we bend out of shape and have it build up like that or bounce up. As the launching process happens, whenever it hits the bottom there, it dislodges it, and then all of the potential energy that is stored there, the elastic forces there, is released and converted to kinetic energy, which launches the thing up. Well, that's sort of like the main thrust of this lesson. But on top of that, you see this wobbling effect there, back and forth, and that by itself is a whole other lesson in what we call resonance. You may have seen or heard that an opera singer might be able to sing at the right frequency and vibrate a wine glass and break it. And that's a resonance, because the sound waves are vibrations in the air, and if you can get the glass vibrating at the right frequency, then it can go out of control and crack or shatter. There have been other cases of even bridges falling down or buildings collapsing, because if the earthquake or some wind or something goes at the right frequency, you can get it into a natural state of motion like that, where it reinforces itself and it can break itself apart. The most common form of resonance would be like a swing set. So if this is like a swing suspended here, if I push it at the right speed, like if I just hit my finger at the right speed, at the right frequency, I should say, then I can have a very efficient energy transfer. In other words, if I'm doing it too slow, then it's not so good, right? If I'm doing it too fast, then I'm almost never hitting the thing. But if I hit it at the right frequency, matching the frequency of this device, it's kind of difficult to do here, the right frequency, what we call the resonant frequency, then I can very, very easily and efficiently impart energy from my finger into the swinging motion. Every physical item in the universe has a resonant frequency. And so this piece of metal does too, because the length of these legs and the elastic force, there's two main things you need to be able to calculate the resonant frequency. You need to know how long the thing is or how big it is and how much mass is involved, because there has to be what we call a restorative force. So when this swing is if we analyze that for resonance, if we push it up, there's a force acting to make it come down, but there's a length to it that makes it want to oscillate at a certain frequency, right? Notice that if I shorten this thing, If I shorten the string, it wants to oscillate at a much faster frequency. You can just see it as it swings back and forth, right? Look at that frequency. And then as I drop it down, notice this frequency. The frequencies are totally different. In fact, if I bring it up, you can see it go faster and faster and faster as I make it shorter. So the resonant frequency is related to how massive the object is, how long the object is, and a few other factors. It depends on the physical system you're talking about. But inside of this paperclip, there's some resonant frequency there as well, because there's a length to it, there's a mass to it, and so on. So as it was triggering, I thought it was fascinating to watch the wobble back and forth at the resonant frequency there until the oscillations dampened out. All right, so that's an overview of kinetic energy, potential energy, and converting between them. Applies to mouse traps, applies to these neat little bouncy things that you can make with paper clips, applies to almost everything in the universe, actually. So I'd like you to please let me know what you think. Please drop me a line. Tell me, do you want more detail, less detail? Tell me what you want. I read every single comment, and I'll see you in the next one. Learn anything at mathandscience.com.